Hi guys, welcome back to my channel. As you can see from the title, today we will discuss different simulation methods, particularly molecular dynamics simulation, Monte Carlo simulation, and density functional theory. So each of these methods is based on different physical principles, operates at different length and time scale, and answers different scientific questions. But after today's video, you will clearly understand that how these methods work, what kind of information each method provides, and when and why one method is preferred over the other. So starting from molecular dynamics, and it follows Newton's equation of motion. So let's begin with molecular dynamics, commonly known as MD simulation. It is a time-dependent simulation technique where atoms and molecules are allowed to move according to Newton's law of motion. You see here, I have put the equation here where the force acting on atom determines its acceleration and consequently its motion over time. In molecular dynamics simulation, atoms are treated as classical particles, meaning quantum effects are not explicitly observed. The force on each atom is calculated from the derivative of the potential energy with respect to atomic position. And once forces are known, atomic trajectories can be computed step by step. If I, if you can see the graph, so we plot atomic trajectories. Before that, I will also talk about force field involved in molecular dynamics simulation, the time integration, and ensembles also. So the accuracy of molecular dynamics simulation depends strongly on the force field used. Like force field, I already mentioned in the previous video that it describes how atoms interact through like bonded interactions such as bond, stretching angle, and torsional angle, and non-bonded interactions, including van der Waals and electrostatic forces. So commonly, force field used in molecular dynamics simulation are compass, force field, foresight, and also UFF also, but I haven't mentioned here. The other thing that is important is the time step. Like molecular dynamics simulations in advance in very small time steps, typically around 1 femtosecond, to accurately capture atomic vibration. You know that we trace atomic vibration. So femto is a very small period of time. And to simulate realistic condition, we use thermodynamic ensembles like NVT, NPT. For NVT, the temperature and volume is constant along number of atoms. For NPT, number of atoms, pressure, and temperatures are controlled, like they are fixed. So what we have learned in molecular dynamics simulation, one thing is it is time dependent. And uh, it is based on Newton's law of motion. You know that I have put the equation as well. And atoms treated as classical particles, trajectories obtained by numerical integration. So what we do, we get a graph and we see how the atoms behave over time. So where we can implement these when we want to discuss diffusion, like where we track how molecules move through a material. Adsorption dynamics, like showing how gas molecules interact with the surface over time, and structural stability, revealing whether a system remains stable under thermal motion or not. Because MD explicitly includes temperature and time, it is ideal for investigating transport properties and kinetic behavior, which cannot be captured by static methods. So it's clear. Now moving on to Monte Carlo and Metropolis algorithm. Actually, Monte Carlo uses Metropolis algorithm, and GCMC is Grand Monte Carlo simulation, which is a type of Monte Carlo simulation. So let us understand this. Monte Carlo is a statistical sampling technique and does not involve time evolution. Instead of following atomic motion, Monte Carlo explores the configurational space of a system using random trial moves such as particle displacement, insertion, or deletion. So it is random statistical sampling. Each trial move is accepted or rejected based on Metropolis method algorithm, which depends on the change in system energy followed by Boltzmann distribution. So if you know the Boltzmann equation, which involves the temperature, you will understand this. So a very important MC method is Grand Monte Carlo simulation method, where chemical potential, volume, and temperature are kept constant. So this is the condition of Grand Monte Carlo simulation, that these things are kept constant. This makes Grand Monte Carlo simulation especially suitable for gas adsorption. Now, what we have learned? We have learned that Monte Carlo is a statistical sampling, no time evolution. It's just energy based, the probability based, explore configurational space, particle displacement, insertion, and these are the energy, how energy and times are involved. So at the end, it is a equilibrium distribution. Now, how and where we implement. Monte Carlo simulations are particularly effective for studying equilibrium properties like adsorption isotherms showing gas uptake as a function of pressure, selectivity gas in especially in gas mixture, and equilibrium thermodynamic properties. And it is important to note that Monte Carlo does not provide dynamic information such as diffusion and kinetics. And it is often used together with molecular dynamics simulation. So finally, we will move on to density functional theory and DFT framework. This is a third simulation method we will discuss today. And DFT is a quantum mechanical approach based on the concept of that the properties of many electron system can be described using its electron rather than many body wave function. The theoretical function of the DFT lies in the Kohn theorems. I haven't put the equation here, but if you see the Kohn-Sham equation, you will understand it better. And while we will be doing tutorials for DFT, you will understand that how important the exchange correlation is. Like it includes local density approximation, which is called as LDA, and generalized gradient approximation, that is GGA for the short form, and hybrid functional. So we will implement these, and how the selection of these are important, you will understand. So what we have learned, it is a quantum mechanical method, EFT, and it is electron density based. Previously, the first one was time based, and the second was random sampling and the energy involved. So here, ground state properties are involved, electronic characteristic reactivity. But for MD and MC, we didn't talk about reactivity. So what happens here, it can also explain chemisorption along with physisorption. The HOMO and LUBO gap are calculated. And the other thing is it also it can also determine that the electron transfer ability of the molecule, that which has acceptance and based on the values of HOMO and LUBO gap orbitals. So what and where we can use these DFT? What are the applications? First of all, we know that DFT is particularly useful understanding electronic level phenomena. So adsorption energy calculation revealing how strongly molecules bind to the surface, like is it chemisorption? Then charge transfer, obviously it's electronic levels phenomena. So we'll discuss charge transfer analysis showing electron redistribution, and HOMO-LUMO analysis, which provides insight into chemical reactivity, that which can release an electron, which can accept. Although it is expensive and limited to a smaller system, provides fundamental electronic side that complements MD and MC simulation. Finally, before concluding, I would like to compare these so that we have the essence of this lecture. So, Monte Carlo, molecular dynamics, and DFTs. First of all, molecular dynamics focuses on dynamics and time evolution. Monte Carlo on equilibrium and statistical sampling, probability based. So, DFT focuses on electronic structure and quantum effects. In modern research, these methods are combined to achieve a comprehensive multi-scale understanding of materials and molecular systems. So that's all. I hope this lecture uh, will give you immense knowledge regarding these simulation methods. Signing out. Allahhumabarik. Bye.